Hey everybody, and welcome to our next video in the Chem 2 review, which is all about electron configuration. So we don't really talk about electron configuration all too much in Chem 2, although the concept of electron configuration is very important for a lot of the things that we talk about. I might ask a question here or there about electron configuration, but otherwise it's not really covered all too much. It is important though, because electron configuration helps us to determine why certain atoms bond the way that they do. Why does carbon have 4 valence electrons and nitrogen has 5? So it's the backbone for that, although we don't actually talk about everything electron configuration in Chem 2. But I do like to review it because it is very, very important. You might be familiar, I think if you had Dr. Clark, you might see a lot of this, but you might be familiar with something like this. So electron configuration, of course, deals with the 1s, 2s, 3s, the 2p and 3d and 4f and etc. But it has to do with where electrons go in specific subshells in atoms. There is so much chemistry that goes into electron configuration, and there's quantum mechanics that goes in there. We're not getting into any of that. But I just wanted to review electron configuration with you. So you might remember when you were filling up those electron clouds or those energy levels to show where electrons go in an atom or element, you have to use the Aufbau principle. And the Aufbau principle says that you put electrons in the lowest energy level first, and then you build up from there. That's why chemists sometimes call the Aufbau principle the building up principle. So if I were to determine the electron configuration for nitrogen, let's say, which has 7 electrons, I would start off by filling the lowest energy level first, which is 1s. Once that gets filled, I fill up the 2s, and my next lowest level to fill up would be 2p. We don't want to start by filling in the 3D subshell first, because we're not starting off at the bottom. We want to build up. So we always want to fill that lowest energy level first by using the Aufbau principle. I don't teach it using the Aufbau principle because you can always determine the electron configuration for an element just by looking at a periodic table. So that's exactly what we're going to do, is I'm going to show you how to determine the electron configuration just by looking at this right here. So I'm going to cut to the notes. I want you to grab about 4 highlighters or 4 colored pencils, 4 crayons, whatever, just 4 different colors. And let's get ready to start labeling this with the different blocks. All right, so if you had me before, you're familiar with coloring in the periodic table just to show the different blocks that we have. We have S, P, D, or F blocks. Like I said in the segment before, there is a lot of chemistry that goes into this. So the S, P, D, and F has to do a lot with the shape of those electron clouds that those particular electrons are in, which we're not getting into. So you don't have to know all of the ins and outs of this, but you should be aware of how to do electron configuration. So what I'm going to do is I'm just going to highlight different parts of this periodic table that's in your notes. And I like this periodic table because it's actually totally updated. So if we look at this 7th period right here, we have all of those new elements, which I really like. So I like to try to put this periodic table in the notes as much as I can. So we have this color pink, and you could pick whatever color you want. Like I said, you could use highlighters or colored pencils. It doesn't matter. But I just want you to label these elements that I just labeled in mine. So it's your alkali metals and hydrogen. You have your alkaline earth metals, and then you have helium. That's a part of this as well. And all of these elements have their outermost electrons in the S block. So those are all your S block elements. You might have to pause this because I'm going to run through this pretty quickly here. And that's okay. Let's pick a different color, and I'm going to color this whole entire section right here. So everything here. You have your halogens in this section. You have your noble gases. I don't remember which group it is. It's either oxygens group or carbons group. I want to say oxygens. It's called the chalcogens, I think. They all have names, but they're not as important because you're going between like metals and non-metals and metalloids. So they all don't have similar properties in these couple of groups like they do in your halogens or alkali metals. These elements here are known as your p block elements. So their outermost electrons exist in the p block. Let's go ahead and pick a third color. And let's do this one here. Looks like a darker pink. And we're going to color in all of these transition metals that are here in the center. And what's interesting about the periodic table is you'll see that there's a couple of like a blank sections right here. And that's because this whole entire piece, your lanthanides and actinides, actually fits right in this section right here. The only reason it's not written like that is because it doesn't necessarily look nice on a piece of paper. But yeah, this whole piece goes right into that section there. I have like a German periodic table I can show you in real life if you're interested. These elements are located in the D block. So those outermost electrons you can find in the D block or the D subshell. And again, there's so much chemistry that goes into each and every one of these, but we're just trying to eliminate the hard stuff and to just do the very basics, like how to do electron configuration. And then we have our lanthanides and actinides down here towards the bottom. And let's go ahead and label this. These elements are in your F block. So if you need more time, you can go ahead and pause this video to color those in. I like to teach electron configuration this way because you could just look at a periodic table and determine what energy level those outermost electrons are in. So if I were to find, let's say, the electron configuration, let's just kind of work through sample problem 5 together down below. So if I go to sample problem 5, write the full electron configuration for each of the following. The first one we're going to do is nitrogen. So nitrogen's right over here. We want to know what's the electron configuration for that element. We're going to start from the beginning because we want the full electron configuration. So we're going to start right here with hydrogen. And we have to know what block each of these elements are in. So that's why they're color-coded. But we also need to know what energy level those electrons are in. So both of these, both hydrogen and helium, because they're in the first period, have their outermost electrons in the first shell. Lithium through neon, these guys have their outermost electrons in the second shell. Sodium through argon, these guys are in the third shell. And then this is true going all the way down. So this period has their outermost electrons in the fourth shell, 5, 6, and 7. We're going to forget about the lanthanides and actinides for right now. So let's figure out what's the electron configuration for nitrogen. Like I said, you can do this using that Aufbau principle, but I don't like to have to memorize something else. I like to just look at a periodic table and figure it out this way. So we're in the S block first. We're in the first energy level. So we're going to start off with 1. So we're in the 1s sublevel because we're in the first row, S block. And I have to pass through 1, 2 elements to get to nitrogen. Now, of course, I'm still not at nitrogen, so I have to continue writing this. 1s2. That brings me to lithium. Lithium's electrons are in the second energy level. All of these elements have their electrons in the second energy level. But to get to nitrogen, I have to pass through the 2s block because I'm still in this section right here. So I'm going to start off by writing 2s, and I have to pass through 2 elements. I have to pass through lithium and beryllium. So 2 for the energy level, S for the block, and 2 because you have to pass through 2 elements. Now I'm still not at nitrogen yet, so I have to continue. Because I'm still in the second period, this is still 2p. So it's still 2, but now I'm in the p block, and I have to pass through 1, 2, 3 elements to get to nitrogen. So this electron configuration would end with 2p3, just like that. So 1s2, 2s2, 2p3. Let's just go ahead and look at this so we could see it. So I have 1s2, first energy level, S block. I have to pass through 2 elements. Then I'm at lithium, 2 because I'm in the second energy level, S because I'm in the S block, 2 because I have to pass through 2 elements. Still in 2, so it's 2p because again, now I'm in the P block, and I have to pass through 1, 2, 3 elements to get to nitrogen. Notice that nitrogen has 7 total electrons, and if I count up all of the electrons that are present in this full electron configuration, 2 plus 2 is 4, plus another 3 gives me 7. That should match the number of electrons that that element has in total. This is the full electron configuration for nitrogen. Let's go ahead and try sodium. So sodium is right here, number 11, atomic number of 11. Because we want to write the full electron configuration, let's start from the beginning. So I'm going to start off with 1s2. 1s2. I still have to pass through this section right here. So this is 2s2. 2s2. And now I have to pass through that P block. So I'm just kind of following the atomic numbers as I go along. Still 2. Now I'm in the P block, but I have to pass through 1, 2, 3, 4, 5, 6 elements. So I would continue by writing 2p6. However, we're not done because that 6 leaves me at neon, and I want to get to sodium. So sodium is the next element over. Now I'm in the third energy level, S block, and sodium is the first element. So I would end this with 3s1. 3s1. And again, you can count up all of those superscripts. So 2 plus 2 is 4, plus 6 gives you 10, plus that last one there gives you a total of 11 electrons. And sodium's atomic number is in fact 11. And because it's neutral, we'll assume that the protons and electrons are the same. So that works out. Let's try chlorine next. So chlorine is here. I'm just going to start writing all the way up to sodium because it's going to be the same. So 1s2, 2s2, 2p6, brings me to neon. Now I'm here at sodium, but I have to pass through that. So I have to get 3s2 because I have to pass through sodium and magnesium. So 3s2. However, we're not done because chlorine is here, still in that third row, that third period, P block, but now I have to pass through 1, 2, 3, 4, 5 elements to get to chlorine. So we're going to end this guy off at 3p5. If you want, like I said, just double check to make sure you have those electrons correct. 2 plus 2 is 4, plus 6 is 10, 12, plus another 5 gives you a total of 17 electrons. And that is, in fact, chlorine's atomic number. right there. Let's try titanium. So titanium is down here. So I'm just going to go ahead and write the electron configuration up through calcium because there is a little exception to the rule right here. Of course, there's an exception, right? It wouldn't be chemistry if there was no exceptions to any of the rules. So 3s2, 3p6, 4s2. That configuration is going to bring me all the way to calcium. So like I said, you can pause this video and do that for yourself, but you can double check your answer here. When you approach the D block, now it starts to get a little interesting because these electrons don't actually go into the fourth energy level. You'll see that even though all of these elements are in the fourth energy level, or they look like they're in the fourth, they actually go in the third. So let's try to get, let's see, let's do purple, I suppose. These electrons drop down and go into the 3D sublevel. In the row below that, guess what that means? These guys go into the 4D, these go into 5D, and these go into 6D. Right there. They go into the energy shell below for reasons that I'm not going to get into right now. I'll be more than happy to explain it to you in person, but this will start making the video far too long, and I don't really feel like doing that for you over the summer. So to get to titanium, I have 4s2, and rather than 4d2, these drop down to the 3d. So I'm going to end that electron configuration on 3d2. 3d2. Add up all of those if you want to just double check to make sure you have the correct amount. And if you add them all up, you should get 22 electrons. Krypton, last one for this section. So here's krypton. Again, I'm just going to go up to calcium again. So if you want, you can pause the video and go up to calcium, but you did it in the one before that, so it shouldn't be too difficult for you to do since you already did it. 3p6, 4s2. So that brings me to calcium, which is right here. I have to continue going through, but remember, once I hit to that D block, we go down to the third energy level. So 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this becomes 3D10. And once I completely pass through there and I'm back in the P block, this goes back up to 4. So this again becomes 4P. Once I go back to gallium, this becomes 5P, 6P, and 7P. So I would end on 4P, 1, 2, 3, 4, 5, 6, 4P6. Like I said, there is so much that goes into this, and that was a really quick overview. I feel like in Chem 1, you either know how to do this or you don't, and if you're taking Chem 2, I'm sure you're comfortable with electron configuration. I'm going to link my Chemistry 1 video on electron configuration if you have any questions, and I go into more detail there about why we do things the way they do. With the way we do them. So if you want to watch that video, you'll see a little bit more of the theory in there. Otherwise, let's go ahead and do sample problem 6. So this is really what's most important, is knowing the electron configuration, because it helps chemists to understand why that particular element has the number of valence electrons that it has. So we're going to write the noble gas electron configuration for each of these elements. So we're going to start off with lithium here. And I'm going to use a different color just so we can identify these. I guess let's do it in green. So here's lithium. And before we do these, we have to, of course, identify where the noble gases are. And your noble gases are always found in group 18. So your noble gases are right there. What you need to do to determine the noble gas notation is to find which noble gas comes before that element in question. So in this case, the noble gas that comes before lithium would be helium. So we are going to write helium in brackets first. So we're going to write helium in brackets, just the symbol. And then we're going to write whatever electron configuration remains after that. So once I'm here, I'm going to start off in the second period. And lithium actually ends at 2s1 right here, second period, S block, first element. So I'm just going to write whatever comes after that, 2s1. And that's it. That's the noble gas notation. This is important because it helps us to determine how many valence electrons an atom has. In this case, there is only one electron in that outermost shell, which means that lithium has one valence electron. And that one valence electron gives lithium the properties that it has, which is what makes electron configuration so important. These right here are your core electrons. So these are core electrons, which they don't really determine how an element reacts. They just help make it stable. And then those valence electrons, these outermost ones, are your most important ones. Let's look at fluorine. So fluorine is right here. So there's fluorine. Again, we want to find the noble gas that comes before that element in question. So in this case, we're still working with helium. Helium is still the noble gas before that. So I'm going to start off by writing helium in brackets. And that just shows us, again, those core electrons, those electrons that are in the energy level below that valence level. And to get to fluorine, once we get to helium, we're going to continue right here at that second period since helium ends in the first. So my configuration that comes after that would be 2s2 and then 2p5 because fluorine is the fifth element in that section. So 2s2, 2p5. And again, you can determine how many valence electrons that particular element has by counting how many electrons are in that outermost shell. In this case, for fluorine, it's the second shell. So this element, fluorine, has 7 valence electrons. Again, which gives fluorine the very unique properties that it has. Let's try argon. So you might notice that argon itself is a noble gas right here. However, even though it's a noble gas itself, you still want to go to the noble gas before. And that's because you want to show those valence electrons. So writing argon in brackets is not correct because you're not showing the valence electrons. You always want to show them. So we'll write neon in brackets, and then we're going to start from there. So I would end with 3s2 and then 3p6. So let's write that down here. 3s2, 3p6. And if I count the valence electrons, 2 plus 6 gives me 8. And you might remember that 8 is great. 8 valence electrons. That's why your noble gases are unreactive, because they already have a full outer shell. They follow that octet rule, which says that atoms want to gain, lose, or share electrons, but they have 8 in their outermost energy level. Argon is stable because it has those 8 valence electrons. Let's try copper. So copper is a transition metal, just all the way over here. So the noble gas that comes before copper is argon. So let's write argon in brackets. and then whatever comes after that. So looks like argon's in the 3rd energy level. We're going to have to start off with the 4th. We would have 4s2, and then we would end with 3d9 because copper is the 9th element. So 4s2, 3d9. Now, if you look up the electron configuration, the noble gas notation for copper, you're going to see it's actually different. In real life, copper's electron configuration is 4s1, 3d10. There's a reason for that. It has to do with the stability of the electron shells. We're not going to get into that though, so you do not have to know that. But just in case you look that up and you're like, wait a minute, that's not what Mrs. Snyder said. Mrs. Snyder said it's 4s2, 3d9. There is something called the lanthanide contraction, and that has to do with why copper's electron configuration might be a little different. It has to do with a couple of elements, actually, but I don't get into that unless you take AP chemistry. I will cover it in that class. But just so you know, it might be a little different. Copper, it's hard to determine valence electrons, so we're actually not going to do it for that one. So we'll just leave that one blank. Why don't you go ahead and try bromine? So really quick, try bromine. What is the noble gas notation? Pause this video, write it down, and I'm going to have the answer here once you come back and watch. And there it is. So argon in brackets, 4s2, 3d10, 4p5. This one is a main group element, which I'm going to go over in the next section really quickly. You always want to count just those outermost electrons right there. So just the ones in the 4th shell. These D electrons, again, the D block gets a little funky, so we don't want to count them for valence electrons. But in that 4th energy shell, I have 2 plus 5 gives me a total of 7 valence electrons. So notice that bromine and fluorine have the same number of valence electrons. That means that they are going to react similarly to one another in real life. Because they have those same number of outermost electrons, they are going to bond and react to similar elements in the same exact way, which I think is really interesting. Using that information, let's finish this off by talking about the types of elements on the periodic table. So the electron configuration can tell us how many valence electrons an atom or an element has. And of course, the number of valence electrons determines the properties that that element has. So we can classify a couple of different types of very important elements on the periodic table based on how many valence electrons they have. Hydrogen, of course, is unlike any other element. It's the first element on the periodic table, has 1 valence electron, 1 electron period. And because it's so small and because it only has that 1 electron, it has properties that are unlike any other element on the periodic table, which I always thought was kind of crazy. Even though hydrogen is in the alkali metal section, which is the next one, hydrogen is actually not an alkali metal. It's just a thing all on its own. If I were to classify hydrogen, I would put it as a nonmetal, but it really doesn't even fit the properties of nonmetal. It's just a complete entity all on its own. Your alkali metals you can find in group 1 except for hydrogen. So like we said, hydrogen doesn't belong as an alkali metal because it's not like any of them at all. Your alkali metals are your most reactive metals. You might have seen me or maybe some videos of people putting sodium metal or potassium metal in water. When you have those pure substance elements, they are highly, highly reactive, especially with water. Alkaline earth metals are right next door. So these guys are in group 2 and they have 2 valence electrons in their outermost shell. You really don't need to know properties about these ones specifically. They are not as reactive as your alkali metals, of course, and they are more hard and more dense than your alkali metals. Transition metals you can find in that D block, so that whole middle section of the periodic table. Those are transition metals. And something interesting about the transition metals is that they form compounds that produce colored solutions. So anytime you're working in a lab and you have, let's say, a blue solution, or you have a green or a purple solution, those solutions most likely contain some sort of dissolved transition metal. You might have cobalt compounds, iron compounds, nickel compounds, which is really cool. Your alkaline metal and alkaline earth metal compounds will not form colored solutions when they're dissolved in water. I always thought that was pretty neat. It all has to do with the wavelength of light. You're going to hear me reference main group elements a lot, and your main group elements are just your S and P blocks on the periodic table. So that has to do with just your alkaline metals, alkaline earth metals, and then going all the way across through the noble gases, and not including the transition metals, not including the lanthanides and actinides down at the bottom. And that's because they vary with their number of valence electrons, and they start to get a little confusing. The main group elements are the easiest to write compounds for, and they're the easiest to name. Halogens, these are found in group 17, and these are your most reactive nonmetals. So fluorine, chlorine, bromine, and iodine, highly reactive nonmetals. In fact, these react very readily with your alkali metals to make salt, or any type of salt. So you might be familiar with table salt, of course, sodium chloride, sodium an alkali metal, chlorine a halogen. They combine to form a salt. But really, any combination of alkali metal and halogen gives you a salt. Lastly, we have the noble gases, which are found in group 18. These guys have a full outer shell of electrons, typically 8, except for helium has only 2, but it still does have a full outer shell, which means it's very, very stable. And the most important thing to know about the noble gases is that they do not react. And the fancy word for do not react is they are chemically inert, I-N-E-R-T. They are inert. So that's our video all about electron configuration. Like I said, I really don't touch on this very often in Chem 2, but it is important to know electron configuration because it is the backbone for why elements react the way they do and why they form compounds the way that they do, which really is what chemistry is. If you have any questions, feel free to reach out to me, and otherwise I will see you in the next video.